So okay, now we know of machine learning as a method for function approximation, right? Let's start to look into how we can use function approximation along with differential equations, and this will start to be this bridge that we call the physics-informed neural network, which we will use to bridge between, this field of scientific simulation and machine learning. So this object, what we'll be talking about right now, actually has a formal name, is called the physics-informed neural network. So physics-informed neural network is where you use a physical differential equation as a regularization term inside of a loss function. So let's actually see how, when you pull this to its basic constituent parts, how a physics-informed neural network is really a method for solving an ordinary differential equation. So this actually dates back. The earliest I can find is actually 1998, where there's this paper on using artificial neural networks for solving ordinary differential equations and partial differential equations. Now, the way to think about this is, so a system of ordinary differential equations is defined by this equation, u prime equals f of ut, where what I mean by prime is I mean the derivative with respect to t, right? Because u itself is a function of t. This is kind of a shorthand. The way that this is a kind of shorthand for what people write as u prime of t equals f of u of t, right? And so the only thing that you can take a derivative with respect to here is this value t, but because you kind of just understand that if t is changing because it's in the differential equation, or if u is changing because it's defined by the differential equation, then people generally omit the of t terms on the u's. So okay, so we have this differential equation which just says when I take a derivative of u with respect to t, I should have this function f for all the t's in some domain. So here I'm going to say I want to solve this in 0 to 1 with some initial condition. To solve this, what we can do is we can say this is a problem where we want to find a missing function, right? What is this missing function? Well, this missing function is the thing such that when I take a derivative of it, it equals f, right? That is a missing function. Right, so we want to find, we let our neural network, nn of t, be something that we want our neural network to approximate u of t. And what that means is that when we take a derivative of our neural network with respect to the input, it should be equal to f of the neural network at that t, right? Because this is by definition what has to be true if this neural network is the solution to the differential equation. Right, so that relationship is 1-to-1. If you find an object that satisfies that equation, right, that a derivative of it equals f, then that object is the solution to the differential equation. And so the problem of solving this differential equation with a neural network is just finding a neural network such that when you take a derivative, you get this f, right? So this gives us our loss function. So what we can do is we can say, here's my neural network with my current coefficients. I can evaluate it a bunch of times t sub I. You can have some crazy training strategy for how you come up with these t's. Let's just say you have some set of t's you want to use. What you do at those t's is you take the derivative of your neural network with respect to its input at those t's, and then you subtract out f applied at the neural network, right, at that t sub I. And you do this for a bunch of t's, you square all the terms, you add them together. Now, why do you square the terms? Well, you square the terms so that way all these terms are positive. So that way, every single time that you have a difference between this value and this value, right, it keeps on adding to the loss. And so when your loss is equal to 0, that means that the derivative of the neural network with respect to time equals the f evaluated at the neural network, which means that it would be the solution to the differential equation, right? So if your loss function goes to 0 here, then your neural network is the solution to the differential equation. Gives us a way to turn solving a ordinary differential equation now into one of these training problems. Now, what do we do about the initial condition, right? Because we don't just have this equation, but we also have that we know what the value is at the start. Now, the way to be able to handle this is to, well, one thing you could do is you could just say this is another loss function term, right? So if I evaluate my neural network at 0, it better equal this term because we said it had to be true. And if it's not true, then there's a positive term in our loss function. So let's make it true, right? That's one way to be able to enforce this. But normally enforcing things through the loss function is not as stable as structurally specifying it. So what I mean by structurally specifying is this idea of generating a test function, a neural network, or this universal approximator, which is in the space of functions, which always satisfies the property that you have. So to see what this looks like in action, this is a very nice case to do this. So here what I do is I can define g of t equals u0 plus t times the neural network at t. When t equals 0, then that means g of t equals u0. And when t is non-zero, then I have a universal approximator added to it, right? So this is a very nice way to be able to construct a function, a universal approximator, which is always u0 at time t equals 0. And this is a universal approximator over the space of continuous functions, right? Because this will continuously change away from u0 at around that point. So you have to prove that this is the universal approximator. I'm not going to prove it here, but you can kind of see how it's going to have that property, right? If you plug in 0 for g of t, you see a equals 0, u0. If you plug in any other t in there, well, then you have a neural network that can change it around. And if a neural network can approximate any function, then g of t can be anything it wants as long as it's not at 0. And so this gives us this structural property that if we use g of t instead of the neural network directly, then we have something that always satisfies the initial condition. And so we can do the same process as above. We define a loss function such that g has to satisfy our, g has to be something that satisfies the differential equation. But by using g, we no longer have to have this this boundary condition term, this initial condition. So let's actually code up the method. Let's actually do it. So we can say, well, I want to have my neural network be something that takes in a scalar and spits out a scalar. So here's a nice trick for doing that. So remember, a chain is just something that calls functions, right? So you don't need to look at the neural network library for how to do these things. You can use any function you want. So here, what I want this to do is I want to have a scalar come in, and I want to put it in an array. Then I want to do some neural networky things, right? And then after I neural network around, what I want to do is I want to, I have one value, but it's in an array. I want to turn this into a scalar. So I take the first value of that array. This is equivalent to doing this, right? So this is then a neural network that takes in a scalar and spits out a scalar. If you didn't use a library, you can probably use static arrays and these kinds of objects to make it a bit more efficient, but this is kind of a simple demonstration. So this is the way to kind of hack the neural network library, understanding what chain does to just make it be something that is now a scalar to scalar neural network. So now what we do is I define this g of t, right? So g is this function that now this is my universal approximator that is something that has to be 1 at time t equals 0. So the differential equation that I want to solve here is I want to solve that u prime equals 2 pi t, where u of 0 equals 1, or u0 equals 1. Okay. So if I want to solve this differential equation, how would I start to define this loss function? Well, what I will do is I'm just using, here I'm going to use finite differences for the derivative as a demonstration. So, right, so just as a reminder, this term right here, what this is doing is I perturb forward by epsilon, then I subtract the value, and then I divide by epsilon, right? This is the definition of the derivative. As epsilon goes to 0, then this converges to being the derivative, and so this is an approximation to the derivative at time t, right? Why I chose epsilon to be square root of machine epsilon, this is something that we'll go into later in the course. So here, what I want to do is I want to for t in from 0 to 1, right? So this is, let's just look at what this is, right? So remember, this is a range object, and so it's not as informative in that form. But if I collect it into an array, I can see all the different values. And so this is, starting at 0, going by 1f minus 2, so float 32 values, and going up by 0.1 all the way up to 1. So for each of those times, what I want to do is I want to take my test function g, I want to calculate its derivative at t, and then I want to check it against the function f, right? So I want to check it against 2 pi cosine of 2 pi t, and this should be equal to 0. And what I'm going to do then is I'm going to take the square of that value. I'm going to have my loss function be the mean of all these values. So instead of just being the sum, I divided by the number of terms. So that way, if I change the number of terms in the number of t's that I'm evaluating at, it doesn't actually change the relative size of my loss function. So here's my neural network training problem. What I want to do then is I want to say use gradient descent. My data, so this is a machine learning problem, but I don't have data, right? So what I'm doing here, this is my little cheat, remember, where I'm saying repeat empty data 5,000 times. So it is training over data. My data is just nothing. And now I'm going to add a callback in here so that way it displays as it's doing the training process. What I want to do in this display is every 500 iterations, I want it to tell me what the loss is. Right, and so before we start, what is the loss of my random neural network? How well is it doing? It is at 4.5 f minus 6. I think. Let me make sure I take a completely random neural network so that way it's not rigged. Right, so my average error here is 0.5 at each point in space. Now what I do is I run the training process, right, which will step 5,000 times, and each time what it's doing is it is trying to minimize what the error between the derivative of g is from the evaluation of f, where f is the differential equation term that I wanted to solve. And after some computational churning, which is a rigorous term, then what we should see is we should get something that solves the differential equation. So let's actually check our output here, right? So if we have this differential equation that g prime equals 2 pi cosine t, well, if we take the derivative of both sides, or if we take the integral of both sides of our equation, then what we get is g equals a constant plus sine of 2 pi t divided by 2 pi, right? That's just the integral rule. And here we define c equals 1. Why is c equal to 1? Well, because that's what our initial condition was. Right? So another way to think about the initial condition in an ordinary differential equation is that solving an ordinary differential equation is just taking the integral of both sides, and you have a arbitrary constant that comes out. The initial condition is the thing that specifies what that constant is. So now let's actually plot this. So if we take a bunch of different time points, right? We only trained on time points 0, 0.1, 0.2, etc. But let's plot on more time points just to see the regularity of our solution, see how well it does. And you can see over on the side from my notes, while the plotting library is precompiling, you can see that it very much matches the true solution, right? The true solution is a sine function that is perturbed. And here what we have as the neural network is something that really closely tracks the sine function. So this is a way then to be able to train a neural network to be the solution to a given differential equation. And now what we can start to do is we can start to use this idea to be able to augment loss functions with physical terms that are physically motivated by these differential equations, these physical laws. And so let's look at doing a harmonic oscillator informed training. So here, let me just kind of make sure that I get the plotting library set up because I'll be using it a bit here. So let's assume that we are taking a bunch of measurements of some spring system. Let's actually take a look at this because I found a very pretty picture on the internet, so you got to use it, right? So here we have a spring system, and as you move the spring away from its steady state, then what you see is that so that this difference between between the spring from its steady state, it induces a force, and that force that you get from the spring is linear, right? This is called Hooke's law, and this is what everyone learns in first year physics. Now this is true for a very idealized spring. What are some things that we had to be true for this? Well, you need to have that you have the same mass throughout the spring. You need to have that there's no frictions. There's a lot of assumptions that are made here in order to make this actually be the physics 101 version of the spring. So the physics 201 version of the spring has extra terms in there because you have deformities in the metal. You have all these other things that can happen. So let's assume that we have a real spring, and our real spring has this extra plus sign term in there, right? Because it's due to having some deformities in the metal. What we want to do now is we want to train a neural network that will be able to tell us what, given an input f, what force we would be expecting at a given point. Right, so we want to train a neural network to be the force function. Now, given Newton's law of motion, right, if this is our force, then F equals ma, and so if we assume mass equals 1 to be able to make our units, simple here, then what we have defined by this force equation is a second order differential equation, x double prime equals minus kx plus 0.1 sine of x, right? So let's take a look at this. So here we can use the differential equation library to be able to tell us what the values would be if we were to solve this differential equation. Hopefully it's not going to have to precompile right now. Sorry about that. And so this is what the solution of this spring looks like, right? So it's something that has a periodic motion, just like the original spring, but it has some kind of perturbation to the way that the force is working, because it has this perturbation in there because well, we're assuming that maybe this part of the spring is less stretchy than this part of the string, so as you start to stretch it around, it doesn't uniformly always have the same force to go back. So if you don't know this differential equation solving syntax, don't worry, we'll be going over it in one of these future lectures. So now let's actually look at what the force is as we are going through the solution, right? So what the solution is looking at is that this blue curve is the velocity over time, this orange curve is the position over time, but what we want to learn is we want to look at the force, right? So what I want to do is I want to plot the force, and I want to plot our data. So let's say we took measurements at every third interval through time. So here I'm going to take very precise measurements just to be able to build a plot, and here I'm building the data set, right? So my data set is take the true differential equation solution, and at these points, 0.3.3, 6.6, 9.9, let's say I have the actual value, so no measurement error. So I take the position out of there, and I take the force out of there. Now let me plot what that looks like, and here I show in the notes that we didn't take it at very good spots, right? So what we get here is we get that our different, the way that our differential equation is defined makes it so that way the way that we got our data, we have forces at terms which are all fairly close to zero. So we didn't take very good measurements, but could we still make could we still have a neural network recover this function by using this data? That's the first question to ask, right? Could machine learning actually do this properly with this data set? So we go, okay, I have my data set, right? I define my loss function, I define a neural network, I define a loss function, and what I do with this loss function is I say, well, you know, when here at each point in time, I know I took a measurement of where the spring is, I know what the force is there, and I know what the velocity is at that point. So what I want to do from my data set is I want to take the position, I put this into the neural network, right? Because the force is a function of position. So I take the position, I put it into the neural network. This is a prediction of the force, and I output the force. Right? So I do this over every point in space, I square it, and this gives me my loss function. With a random neural network, this doesn't do so well. And if I do gradient descent, hopefully it does better. Right, so it trains a bit, and now we can see how well our neural network does. And we see that in some cases, yeah, it can do okay, right? But it doesn't really capture all of the physics in there, right? It doesn't really capture what the peak is very well. And the reason is because we don't have data at the peak. So we need to have some way to be able to use the information that we know about physics to be able to supplement the data that we have from the physical system. And so what physical information can we use? Well, let's scroll up a little bit. Oh yeah, we mentioned that, you know, if we have a spring, the first thing that, you know, you learn in your, you know, first physics course is Hooke's law. So you know that Hooke's law should be, you know, for the idealized spring, this is what you'd expect. So let's use that as a starting point then, right? We can say Hooke's law is approximately true, right? It's not completely true, but it's a good approximation. So we want to have our neural network be something that is use the data, but kind of nudge it towards Hooke's law. You know, let's do a mixture of being an idealized spring and something that matches our data points. So the way to do this then is, you know, so let's actually look at how close Hooke's law actually gets on our system. So if we actually look at a solution to the system where we say, you know, we drop that extra term, it's not quite there, right? So it's not a great model, but it's at least kind of it's in the right direction, right? It has the right structures. So what we can do then is we can say, well, let's have a term in our loss function, which when that term is 0, the neural network is something that completely satisfies Hooke's law, right? It is something that solves the differential equation. And the way that you do that is precisely what we did before, right? Where, you know, here we have a domain of times from, 0 to 1. And so here's a way to, here I'm going to take a bunch of random values from -1 to 1. Well, we have we have a domain of positions where all these positions are between -1 to 1. So what I want to do is I want to take a bunch of random positions between -1 and 1 and evaluate the force at those points, right? So how do I do that? Well, what I'm doing is I'm taking a random value from 0 to 1, I'm timesing it by 2 to get a random value from 0 to 2, and I'm subtracting by 1 to get a random value from 0 to 1, right? I do that 100 times. So now what my loss function is what I'm going to add is this term for, are you the solution to the ODE that is Hooke's law, right? And so that's what this term does here. So what I do is I want to loop over my random positions, and for each random position, take the neural network, you know, the thing that comes out of it should be interpreted as the force, and see how close that force is from what Hooke's law would give out. Right? And on my random, for my given neural network right now, does not do very well. So let's assume that, you know, I mean, you did your physics first course, right, where you probably had to do this exact lab where you measure K on some idealized spring, well, on some spring in a lab. And so let's assume that you know K, right? We'll not, you could figure out K on the fly here, but let's start for now today by saying you figured out K from a lab. So you can write down Hooke's law here, where you know what K is, And we now have two terms for our loss function, right? We have one loss function term, which is how well are you actually fitting the data that we need to fit. And you have another term, which is, well, we know physically that this thing should kind of be an idealized spring, so here's the physical laws it should satisfy. And what we can do now is we can say, we can put a weight in there, we can say, we care more about matching the data, but you should also understand this physical law if we don't have any data nearby. And so this composed loss function is then the one that we want to satisfy. And now we do exactly the same thing as before, right? So this is the loss function, which has the universal approximator underneath it. Let's find the weights of the neural network such that we satisfy this loss function. And when we do this, we can then, after training, we can take all of the positions, right, like a whole span of positions, and then we can use that to be able to calculate what the force would be at each of those positions. And now let's actually look at what we can use that to be able to look at what the neural network kind of is as a function, and plot it against the predicted force. So, right, so this predicted force is what the neural network is outputting as what the force is, and the true force is the force that comes from our differential equation. And what we see here is that it's not perfect, right? But this is much better than what we had before. What we had before was something that hit the data points well, but it didn't really know more than the data points, right? And what we kind of fed it is, well, you should take into account how strings act generally because of this physical law. And so what we get is we get a mixture between please match the data points and please be something that please match the data points and please be something that is kind of uses this physical law, which isn't exact, but it's something to kind of base your as a starting point, right? And the solution then is much improved, and this is what we're then calling this physics-informed neural network, because it is not the straight neural network trained from data. This is a neural network that is trained from data that is mixed with the physical law. And so this is really, this is our first direction in scientific machine learning, where, what we motivated, the way that we got here was that machine learning was not a process about predicting data, but it's a process about learning arbitrary nonlinear functions, right? And that is a very powerful idea, right? So there's so many times where you can specify a mathematical problem as find the function such that, and machine learning is the process for finding said function in very high dimensions. And we can start to then, if we understand it as just function approximation, then we can start to use this function approximation in neat ways, right? So here we didn't have very much data, but we can supplement that data by saying this neural network should be the object, which also is the function that solves this ordinary differential equation. So then we can, put these ideas together and say, I have this mechanistic differential equation for how a spring works. Use that idea plus this data, and this weight between the physics idea and the data is what you should be neural network. And then we can, this way of doing it makes it a very well-defined optimization problem, where we then find the weights for the optimization and train a neural network that can perform better than the data that we have on hand by using the extra physical information on hand. So this is the physics-informed neural network, and we'll be doing a lot more scientific machine learning, digging into different methods, but this is essentially, deep learning in a nutshell, and how we can start to move towards putting physical information into the way that we do deep learning.